Local smoothing or local regression differs actually from the spline approaches that we've looked at previously. Local regression is an approach that seeks to fit flexible nonlinear functions using only the nearby training observations around some target point. And it's illustrated in the figure shown here. So let's focus on the point U. We want to provide a smooth function at the point U, and we obtain that by fitting a weighted least squares line where the weights correspond to the height of the kernel function shown by the dotted line at the base of the plot. And what these kernel functions do is they weight observations according to how close they are to the observation of interest at this, the point of interest, in this case, point U. The estimate at point x equals v is obtained similarly and also illustrated in the figure. So we obtain another one here where we fit a line, again, a weighted least squares line, using this kernel to determine the weights. So what we're going to do, the principle of local regression is we repeat this procedure over a grid of x values, and that results in the smooth curve shown. So the principle is quite simple. We're just going to fit lots of local regression curves and connect them, and we're going to weight those regression curves according to a kernel that weights things by how close they are to the point of interest. So in general, at any point of interest, the smooth can be obtained by fitting a degree p polynomial model using weighted least squares with these so-called kernel weights, where the kernel function k is a symmetric positive function which increases as the absolute value of x increases. Now in this kernel, b is the smoothing parameter, it's greater than 0 for local polynomial smoothers, and that's referred to as the bandwidth. And the value of the curve estimate is the height of the fit of beta, where beta minimizes that expression there. It might be clear to understand this just by going through it as an algorithm. The way local regression works is we want to fit a local regression at some point x equals x naught, say. So we select the bandwidth such that data points who are closest to x naught are gathered together. That's the bandwidth we select, and we'll look in a minute at how different bandwidths can affect things. We assign a weight to each point in this neighbourhood so that the point furthest from x naught has weight 0 and the closest one has the highest weight, and we do this through some kernel function, let's say. We then fit a weighted least squares regression of the y on x using the weights derived from the kernel process and the minimization problem stated above. That's just a weighted least squares regression problem. And the fitted value of x0 is then just given by the fitted value of the regression function at that point. Now the weights that we use will differ at each point of interest, and therefore in order to obtain the local regression fit at a new point, we need to fit a new weighted least squares model using the same minimization criteria but for a new set of weights. In order to perform local regression, we need to choose p, that is this degree, and we need to choose b, that is the bandwidth. Practical experience says that p equals 1 works well if f appears to be monotonically increasing, and otherwise p equals 2 is usually satisfactory. And if you want an automatic process to choose bandwidth, you can use cross-validation. So this is quite a quick part of the lecture. It's not, there's nothing that we need to really look into in depth regarding local regression. I want to show you how it works in practice. So we're going to use it to fit the OpenAIRE data. This is the command in R that fits a local regression. We're going to fit the local regression first of all with a span of 0.2. That is going to specify that each neighbourhood uses 20% of n to fit the local regression. And then we'll fit one where the span is 0.5, and so 50% of n is being used to fit the regression. We are going to plot the results, get our predictions, and place these on the graph. And here we have. So we've performed local linear regression using spans of 0.2 and 0.5. That is, each neighbourhood contains 20% or 50% of observations, weighted by kernel, and it gives us this nice fit here. As we can see, the larger the span, in the case of the blue line, then the smoother the fit that we obtain from the local regression. So a different principle actually than regression spline, but actually the results we ended up getting very similar, but is a different approach and one that is certainly suitable in certain settings.